Okay, so we are in section 2.4, and we are actually doing math modeling in this section. What is math modeling? Well, of course, that's the title of this course, Introduction to Math Modeling. But what we're doing is we are taking a real-world situation and we want to write a formula and for that situation. And in this particular section of our textbook, we're dealing with linear functions. So we're going to be looking for formulas for linear functions that are modeling something that's being observed. Now, I want to go into the homework, and because these are application problems and they can be kind of tricky, so I want to discuss that by looking at your homework problems. And let's see, here we are. Question 1, we are asked to write a symbolic representation, that just means a formula, for a linear function that computes the following. So here we have a verbal description of our function. The long distance phone bill is in dollars, and it's for calling T minutes at 20 cents per minute and a fixed fee of $4.95. So what we're going to do here is we're going to notice that, first of all, our variable is T minutes, and our function here is called F. So F is dependent on T. T is the independent variable. And we could, call the phone bill, I don't know what you want to call it, but they're just saying F of T. They're not giving us a dependent variable per se. But we are told that the calling is 20 cents per minute. So your input is the number of minutes that you've spent on talking on the phone, and the fixed fee is just to make the phone call before you spend any time. It's $4.95. So 20 cents per minute, that per right there, cents per minute, it shows you here that the dependent variable is the cents and the independent variable is the minutes or the time. And so cents per minute, and the 20 just is the slope of our linear function. And the 495 is the starting point. And so when T equals 0, your dependent variable is 495. That just means that 495, 495 is a point on the graph, which means this is the y-intercept value. So you're just going to plug in 495 for your constant here, and your slope is 20 cents. Now, you probably want to convert this, since this one is in dollars, you want to convert the 20 cents to dollars, which would be $0.2. And so we have here, the slope is 0.2, and then the intercept value is 495. Okay, next one. We have a numerical data here. So in the previous question 1, we were given a description of the function. Now we actually have numerical data, but we're still looking for a symbolic function for that, symbolic representation of the function. And so we want to find the slope. We're told that it's linear. So we want to find the slope, and we want to find the intercept to get that formula. So if you'll notice that the function values are decreasing. So we know our slope is going to be negative. So it goes from 12 down to 5, and that decreases by 7 units. And then the x values, which is the run, they're going from -2 to 0. So they're increasing by 2 units. So our slope, which is the rise over the run, is going to be -7 over 2. All right. And here, if you look at this point, when our x value is 0, the output, your function value is 5. So that means 0, 5 is the y-intercept. And so we know the slope and we know the y-intercept. So we're going to go ahead and put that in. And plus 5. All right, so our next question, question 3, we're asked to write a formula for a linear function that models the situation. Again, we have a description, a verbal description. A stone is dropped from a water tower and its velocity increases at a rate of 32 feet per second. The stone hits the ground with a velocity of 288 feet per second. So right there at the starting point, when you're holding that stone, the velocity is 0, right? So when the time is 0, then the velocity is 0. So 0, 0 is the y-intercept. So our function is just going to be the rate or the slope times the independent variable, which in this case is t instead of x. So notice it said 32 feet per second. It's increasing at a rate of 32 feet per second. Whenever you see that per, it means you have a ratio. And in this case, we're having feet over or distance over time. Okay, that's velocity. And that is the rate of change, which is the slope of your linear function. So in this case, it's increasing at a rate of 32 feet per second. So our slope is a positive 32. Okay, and we already determined that the intercept was 0, the y-intercept value. So we have 32 times t, that's our independent variable. And we got that. Okay, so let's look at what does the input variable represent? And the input variable is your time. And then state the domain of the function. Well, think about it. At the start, the time is 0, right? You're getting ready to drop it, and the time that you let go, that's your start time. And then at the end is when it hits the ground, and it's at a rate of 288 feet per second. So you're going to have to find out what your time is at 288 feet. So if you take 288 and divide it by 32, let me calculate that. I did not do this ahead of time. So I'm going to take 288 and divide it by 32, and it's going to give me 9. That means that the stone that you dropped has been falling for 9 seconds, because 32 for every second, right? And we had 288 feet altogether. So that means it took, if you divide 9 into that, I'm sorry, if you divide 32 in that, that gives you 9. So that is our domain. So going back, we're going from 0 to 9. And then question 4, I'm going to end the video here because I think I have a limit of 7 minutes. I'm not sure how long I've been talking, so I'm going to end it here. Let's see.